Good afternoon again. My name is Tom Sawinski, and I'm a program manager in the Department of Energy's Office of Nuclear Energy. Today I'll be presenting on the Nuclear Energy University programs RC-5 and RC-6 work scope areas. Thank you. The RC-5 area will focus on experimental validation of high-temperature gas-cooled reactor simulations, and the RC-6 area focuses on two scopes, which is related to fluoride salt-cooled high-temperature reactors. For the RC-5 area and the RC-6 area, the federal point of contact is Diana Lee. Diana is unable to attend today, and I'm filling on her behalf. The technical point of contact for RC-5 is Gerhard Stridum, and the technical point of contact for RC-6 is David Holcomb. I believe David Holcomb will be on the line at the end of this meeting, take any questions you may have. Since I am speaking on behalf of Diana Lee today, I will ensure that any questions you have on this work scope area are recorded and answered for the good of the group, as has been done for previous presentations. I'm going to begin with RC-5, which focuses on experimental validation of high-temperature gas reactor simulations. This particular area is focusing on two scenarios of interest to HTGR core designers and safety analysts. And these involve disruption of the nominal helium flow rate and a transition to what's called either a pressurized or depressurized conduction cooldown event. The pressurized conduction cooldown event is generally initiated by a helium circulator or turbine trip, while the depressurized conduction cooldown event is generally the result of a slow depressurization after a leak or break in the primary pressure boundary. Most HTGR reactor systems incorporate either a water or air-cooled reactor cavity cooling system, or RCCS, as a final heat sink and protection of the vessel and concrete refinement structures as a mitigation strategy for these type of events. For this particular scope, we're focusing on work that entails the evaluation of two particular elements, which is either degraded or asymmetric RCCS performance and a plenum-to-plenum natural circulation characterization. We're looking to characterize the impact of these degraded and asymmetric operations on localized vessel and concrete temperatures. Also looking at an assessment of the impact of slow, medium, and fast blowdown scenarios. Also focusing on natural convection regimes relative to the break location, and experimentally characterizing low velocity plenum-to-plenum gas flow at prototypical conditions. It's important to note for this particular area, all experiments must be performed to NQA1 standards. Data experiments and calculations will be submitted to the Idaho National Laboratory's NGMP data management and analysis system. And it would be beneficial for the applicant to seek assistance from the Idaho National Laboratory to use the management analysis system and to ensure that NQ
You'll start the slide over.
Absolutely. Yeah. So apologies for the technical difficulty. I'm going to restart. We're focusing on RC-6, and this area is focused on fluoride salt-cooled high-temperature reactors. RC-6.1 is focused on optimized fluoride salt pipe joints for fluoride salt cooled high temperature reactors. Flanges that require repeated sealing along with thermal cycling for service conditions above 500 degrees Celsius with low internal pressures still remain a substantial engineering challenge for FHR designs. Differential thermal expansion of multi-material systems frequently results in leaks. Resilient metal seals require precise surfaces to achieve and maintain a seal, while other designs rely upon internal pressure to force a compressible seal into a mated backing. Historic molten salt reactor programs have relied upon frozen salt gaskets, which are not testable prior to filling, along with high temperature bolting. Optimized fluoride salt joints are sought that are suitable for both large and small pipes that can be repeatedly joined and disconnected, can be tested prior to filling with salt, unlike legacy applications, function when subjected to repeated thermal cycling, do not require internal pressure for sealing, and are tolerant of common engineering tolerances, such as the roughness and alignment of the mating surfaces. Due to the relatively early stage maturity of fluoride high temperature facilities and the significant resources required, we realize that establishing an NQA1 program for this particular area may not be feasible. However, priority will be given to experiments that are able to be performed to NQA1 standards. Finally, I'll be discussing RC 6.2, which is related to pump scaling technologies for fluoride salt-cooled high-temperature reactors. Pump shaft seals and oil-lubricated shaft bearings are among the most problematic technologies that were experienced during the molten salt reactor experiment, with hydrocarbon lubricant leaking into the fuel salt, causing a wide range of undesirable impacts. Also, as fluoride high-temperature reactor technologies progresses from the laboratory industrial scale, its component technologies need to scale as well. Long-shafted cantilever pumps are the currently leading candidate for larger scale FHR primary pumps. Gas foil seals, which avoid hydrocarbon lubricants, however, require precise, well-aligned shaft and seal surfaces, which are more challenging at scale and in practice require bearings within the salt. Fluoride salt-compatible bearings remain largely unproven. The scope looks to develop and demonstrate salt pump component technologies such as seals and bearings. These components should address these issues and should be scalable from laboratory to industrial scale, should be compatible with fluoride salts, should prevent contamination of the salts, and minimize radionuclide releases. Once again, due to the relatively early stage of maturity of FHR facilities and significant resources required, we understand that establishing an NQA program may not be feasible. However, priority will be given to experiments that are performed to NQA1 standards. With that, that is the end of this presentation, and I will attempt to answer any questions you have or log them accordingly and provide you answers in a timely manner. Thank you.
We'll take questions over the next few minutes. Please do enter those on the GoToWebinar app. We'll wait about 30 more seconds for any additional questions. Tom, is there a desire for a pump manufacturer to be involved?
I believe this is in reference to the RC-6 category. I don't believe I'll be speaking on a line that if there are abilities for the applicant to show a correlation with available technologies to fulfill these needs, that would be beneficial. similar to the other categories where engagement with industry and their capabilities and needs to address these issues would be encouraged.
We'll stay on the line just for a few more minutes. Tom, going back to a few previous presentation for the RC2 category,
Yes.
do we need to introduce or develop new materials, or are we doing tests on existing materials?
Is this in reference to,
All right, for the microreactors is what the scope code is. That is a materials question though. Oh, sorry, on 6.2. That's what he meant.
that I would have to defer if either David Holcomb was on the line or we can get an answer to that question offline on that.
We don't have David Holcomb on the line, but we do have Luke Walls, who works closely with David. I will put him on the line.
Sure.
Lou, are you there?
I am here. I am here. So it's certainly a preference to be able to use available structural materials for the external boundary of the salts. But as far as internal materials, we're open to any application, any new material, coating applications that would help with bearings and seals. They're going to be, it's just expected it's going to be a specialized material. So it's certainly okay to explore that. Campaign is doing some work in this area, looking at things like galling tests and some tribology testing. But at this point, that data isn't ready to inform design.
Okay. Thank you, Lou.
Okay, those are all the questions we have. We will return at 3:30 for our final technical presentation of the day on the advanced sensors and instrumentation, NEAT work scope area, and the cybersecurity area. And then we'll have some overviews of our infrastructure FOA and our NSUF program after that. So please join us again at 3:30. Thank you.